Hi, my name is Galen Tunnicliffe, and today we're presenting about Lab 3 magnetic field of a bar magnet. Okay, for a quick intro, our objective is to measure the magnetic field of a bar magnet and understand the relationship between the magnetic field and observation distance. Some principles are the Biot-Savart law, which is the magnetic field, and then the concept that the magnetic field is inversely proportional to distance from observation. The results that we got in the end were that the magnetic dipole moment was 8.2 amps times meter squared. The experiment procedure was that we used a magnetic field measure app. We had to calibrate it, and we had to make sure that we compensated for the Earth's magnetic field by making sure that the x and y component of the magnetic field zero by rotating your phone. We had to use a magnetic chip in our phone to measure the distance. We found the distance where the x component had a magnitude of 20, 70, 120, and 220 micro teslas. And we repeat for off axis. So here's just a little graph of what it looked like for our results. And some calculations, ln of k, we got negative 13,318. For our k, we got 1.645 times 10 to the negative 6, that's just the constant, using that formula. And then we ended up with our mu as 8.225, and then our n as negative 2.47. The model known was that the closer the magnetometer is to the magnet, the stronger the magnetic field. Okay, so here's our code for GlowScript. So essentially we just created a magnet at the origin, and we inputted our mu mag over there, and then we just created a cylinder using that magnet, and then down below we defined the dipole using our mu value and our radius. And then now we had to make an arrow at each of the observation points. So we just created vectors describing them. In the cyan would be the perpendiculars, and then in the green will be the on-axis ones. So there's 2 on-axis, and then 4 perpendiculars. Okay, here we did the 45-degree one, which ended up being 0.1987 away, because that's what the numbers crunched to. So we just used that times square root 2 to get the distance. And then observation at the 45 degrees was what it ended up being. So here's our results. So the purple, as you see, is the 45 degrees. The greens are the on-axis, and then the blues are perpendicular to the axis. So the modeled magnitude of the magnetic field at 45 degrees at distance d, we got 1.8477 e to the e negative 5, and then 5.54328 e negative 5, and then 0 teslas. The observed magnitude of the magnetic field was actually 1.99 e negative 5t, so that's pretty close for the x direction, but then 1.7 e negative 4t for the y direction, so that's probably due to some error or inaccurate measurement due to the Earth's magnetic field, due to other objects and surroundings like a human error or like a computer or something. So what if we hadn't oriented our experiment to compensate for magnetic north, and it had instead just laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? Our results would have been way more skewed because they would not have accounted for the Earth's magnetic field, and it wouldn't have canceled out. If we were to stick 2 identical magnets together end to end and run the experiment again, I would expect our results to increase by a factor of 2 due to from the original due to having 2 magnets, but this doesn't necessarily account for the interaction between the 2 fields. Okay, and that's my whole presentation. Thank you for listening.